Right, well, let's get started. Maybe if I move that on the other side. Right, so hopefully the only thing that's visible at the moment is the Things to Note screen. Right, so there's a couple of things I wanted to say, some of which I kind of forgot to put in the week 2 preview. I'll talk about them now. So, as well as all of these lecture slides and videos that go along with them, there's going to be a bunch of course notes. The course notes have quite a bit more detail than the slides in some cases, but the notes are getting a little bit old, so I need to upgrade them. And in some cases, the notes might be inconsistent with the slides. So I will need to try and fix them so that they're more consistent. And once I've done that, I'll put them all up. All right, quiz 1 is out. About 90 people have done it so far. It's due before midnight Friday. Please do it. If you don't do it, you don't get any marks. Remember that it's assessed. It's worth a small number of marks. And you can resubmit. Dropping and enrolling. A lot of people have dropped the course. Well, I shouldn't say a lot. Sounds like everyone's fleeing. But a few people have dropped the course. Everyone who asked, I've marked as an ex-student. But WebCMS seems to have issues with ex-students. And one thing it will do, even if you're an ex-student, that Comp 9315 still gets displayed. I'll have to debug that sometime. All right. And I think I've pointed out the difference between WebCMS as a database or a table of who it thinks is enrolled in Comp 9315. That database is maintained independently of MyUNSW. So what appears in MyUNSW may not yet appear in that database. How many times can you submit quiz 1? As many times as you like. And I've noticed a few people seem to be a little bit lacking in Unix skills. So if your Unix is a little bit rusty, could you not use LDAP as a set of foreign what? I suppose I could. Right, that would require more WebCMS hacking than I'm willing to put in at the moment. I've got enough to do with this course and a bunch of other admin stuff. One day, but that's a good idea. I will take a look at doing that. So if your Unix skills are rusty or non-existent, then you might want to consider having a look at some of the home computing stuff. It's really basic, but some people don't know the really basic stuff. And when I try to talk to people using screen sharing on Zoom sessions, it's very hard to convey what I'd like them to do unless they can feasibly give me control of their screen. I've done that once. I assume the person who did it had a decent network connection, but but the other people I've talked to didn't, so I couldn't really manipulate their terminal, which means I had to tell them what to do. And not only potentially is language a problem, but lack of understanding of Unix is a big problem. All right, let me see. So let's take a look at some of the exercises for this week, unless there are pressing questions. Oh, actually, one thing I wanted to look at, point out, you know, if things are coming due, they're going to appear right here, so you can't complain, oh, I didn't know the quiz was due. It tells you right there, so keep an eye on that. Everything that's due, like assignments, quizzes and so on, are going to appear there. The other thing I wanted to have a quick look at was what you told me about your DBMS experience. Well, that was too slow. Did you see that? That bit of database access took way too long. Oh dear. It looks like the number of MySQL users and Postgres users is about even. A couple of people have used Oracle. One person has used DB2. I'm surprised. A few people have used MongoDB. SQLite, a few people have used. And disturbingly, I have never used a DBMS, 22 people. The question I would have is, why are you doing this course if you don't know what a DBMS is and how it's typically used? I'm kind of assuming that you've at least run some SQL query. How different is Maria from my? Good question. I have a feeling Maria is a derivative of MySQL. I know MySQL got taken over by Oracle. Maybe MariaDB is the continuation of the open source side of MySQL, but I might be talking complete rubbish there. Anyway, right. So one thing that I've talked about was the cost of manipulating relations or manipulating tables in SQL, and that's an important aspect of the rest of the course, in fact. And one of the major points is named after, yes, thanks. One of the main points is that whenever you're getting data for a table off the disk, you always get it in fixed size blocks, and typically 4K, 2K, 1K, 8K, something like that. So you can't fetch a single tuple. If you need to get access to a tuple, you've got to read the page that contains that tuple and then look inside the page to find the actual tuple data. All right, so everything's happening in terms of page reads and page writes, and those operations are expensive. Okay, so to read one page on a typical hard drive takes that amount of time. And writing is similar. Now compare that to memory access, which is in nanoseconds, and you can see that the amount that you can minimize reading from the disk is going to give you a big win in database performance. All right, but here's an exercise. So we've got a table with 10,000 tuples. Yeah. So remember that in one of the videos, I talked about these characteristics of tables. So R is the number of tuples in a table, the number of visible tuples, if you like, the average size of tuples, which may or may not be meaningful. If tuples are all constant size, sure, it's meaningful as soon as you throw in varchars and texts and things like that. Then the size of tuples becomes variable, and even talking about an average size may be a bit iffy. Data pages have a fixed size, which we call B, may vary from DBMS to DBMS, or even from the configuration of DBMS to a different configuration of the same DBMS. You can set the page size in postgresql.conf, I believe. And if you can't set it there, it's certainly defined somewhere in the source code, so you can modify the value. Time to read a page, okay. Time to check a tuple, microsecond, that's probably being exorbitant nowadays. It's probably even. Yeah, all right, I'll think about doing that. So far, I've been preparing this stuff just before the lecture, so it's not really feasible to upload the slides, but before the session, but I'll try from now on. Certainly, these exercises will probably run into Thursday, so that's that should be okay for the later exercises. All right, so these costs of manipulating a tuple once it's loaded in memory is minimal compared to the cost of reading a page of tuples in the first place. All right, so what we're asked to do, calculate the total time cost for answering a query like this. So essentially what we're doing a select from an existing table R, and we're using the result of the select to generate a new table S. So there's going to be cost of reading, obviously the cost of reading from R, and the cost of writing pages into S. So let me quickly switch my sharing to the screen where I'm going to work stuff out. Okay, which hopefully is this. Good, looks all right. I'm not going to make the same mistake I made last time, where I had tabs in the terminal window, and apparently if you got tabs in your terminal window and you switch between tabs, it drops the sharing, whereas it's different in a browser. It doesn't seem to drop the focus. All right, so this is exercise 1. And a lot of these I've already worked out the solution, so I'll just work through them. Typing them up takes too long. Typing them up on the fly. All right, so we've got 10,000 tuples, 200 tuples per page. 200 bytes per tuple. That's critical. And that's the size of a page. So the first question we need to answer, how many tuples can we stack into a page? 4096, well, 200 doesn't divide into 4096 exactly. It might be 20.5, but you can't have half a tuple. So often you'll see that we use floor and ceiling for these things. So if we can fit 20 whole tuples plus half a tuple, we ignore the half tuple, which is kind of meaningless, and just talk about the total number of whole tuples that we can put in the page. So that's the number of tuples per page, which I normally denote as C for capacity. Once we know how many tuples per page, we know total number of tuples, we can work out the number of pages. In this case, it's 500. Notice here we have to use ceiling. So if it turned out to be 499.5, you can't have 0.5 of a page, so you need to round up to a whole number of pages. So it's 500. In this case, we don't have to do any rounding because 10,000 divides 20 exactly, and hopefully the result is 500. All right, so we have 500 pages in the input table R. Probably should have used a different name so as to avoid confusion with that, but too late. That's what the exercise had. All right, time to read a page, 10 milliseconds. So when we're doing our select from R, assuming we don't have an index, we're going to need to scan the entire table and then look at each tuple in each page and decide whether that tuple satisfies that condition there. So we're going to have to read 500 pages. And the time to do that is the number of pages read multiplied by the time to read each page. So that'll be 5 seconds in this scenario. Right, the cost to check all of the tuples, where we have to check 10,000 tuples. Every time we read a page in, we've got to check all the tuples in the page. So we're going to check 10,000 tuples. The cost of checking a tuple is that much, small because it's in memory. And the total cost is 10 milliseconds or 0.01 seconds, which is way, way less than that, even though we're doing this operation a lot of times. All right, number of tuples in the result. Well, we know it's going to be 5,000 because the question somewhere says 50% of the tuples satisfy the where clause. So we're going to write 5,000 tuples into the result. When we fetch a tuple from R and we then insert it into an S, we need to make a tuple structure to place into S, into a page of S, and that's going to cost, so we have to make 5,000 tuples. I guess you could argue, I'm not going to go back to the question, where is it? Oh, here. So we're actually, the tuples that are going into S are actually the same as the tuples that are coming out of R. Even so, we still need to make a new tuple, but certainly if this wasn't star, if it was select AB from R, where X greater than 10, we definitely have to make new tuples that just contain A and B. So once again, the cost of building tuples in memory is vanishingly small. And similarly for the checking tuples, vanishingly small. Oh, I've lost my chat. Oops, hopefully there may have been messages. Yes, there was a new message. Blah, blah, blah. Has my OS cached the table file in memory? It probably has. I'm ignoring this fact for the purposes of this analysis. If it's the first time we've read this table, then it's not going to be cached in the operating system file buffers. So I'm assuming that we're going straight from the disk into the DBMS's buffer pool for the purposes of this exercise. All right, so each time we read in a tuple from R that satisfies this condition, we need to make an output tuple. That's how much that costs. How many pages do we end up writing? Well, the tuples are the same size as the input tuples. Therefore, the number of tuples that we can fit per page is the same as in the input file, and therefore we can calculate the total number of pages that we need to write out. Okay, so it's obviously going to be half the number of input pages. Now, of course, if we had variable sized tuples, we'll be talking about them at some other time, it would be a little bit more difficult to analyze the cost because the number of tuples that you can stack into a page depends on how large each of the tuples was. And maybe all of the tuples that satisfy this condition happen to be very large. So the average tuple size for the result tuples might be larger than the average tuple size for the input tuples. All right, in any case, so we write out 250 pages, 10 milliseconds per page. That's 2.5 seconds. So the total time to read all 500 pages of the input file, time to write all 250 pages of the output file. Guess I should have put units here. And if we add all that up, we get roughly 7.5 seconds, 7.52 if you really wanted to do that, but we can forget about that 0.02, I would suggest. Okay, so that's actually quite a lot. This is actually a worst case scenario where we assume that we always have to read all of the pages. Now this gets back to Curtis's question to some extent, because DBMSs typically have a large number of buffers, and it's possible that a lot of the pages or some of the pages for table R might already be in memory, and so we may not need to read all 500. So that would change the cost. Generally though, since we're writing brand new pages, we can't really avoid having to write 250 pages. I guess one point to make here too is that we're not doing 5,000 writes. What we're doing is each result tuple gets stacked into a page buffer, and when that page buffer fills up, we then do the write. So this is really how many pages are going to be written is 250. So the number of writes is 250, not 5,000. All right, any questions on that? I can leave it up before I jump back to sharing the exercise questions. Got to type faster. Would the writes actually be synchronous? Yeah, all right. Once again, if you've got an operating system there, then I guess, what exactly do you mean by synchronous? Certainly the write, under the assumptions I'm making here, every time you do a write of a page, all of the values in that gets flushed to disk. Would you observe that 2.5 seconds? Oh, okay, I see what you're saying. Maybe not. When the operating system is sitting in the road, so maybe from our database buffers, then when we say write, what actually happens is it ends up in a file system buffer and may or may not be pushed straight to disk. So yeah, you're right, you may not observe the 2.5 seconds. So really we don't tend to talk about things in time units. What we tend to talk about is number of pages read and written, and that's really going to be the cost of our database operations. Does the 7.5 seconds include the flushing to disk? Really, why do you think it would take way less than 7.5 seconds? Unless you're talking about the page reading cost not being 10 milliseconds or whatever. Sure. All right. So as I said, we're ignoring the file system access costs. We're ignoring the fact that there's a layer of buffering between the DBMS and the file system. And basically because of that, I'm not going to deal in terms of seconds anymore. I'm going to deal in terms of number of pages read and written. That allows us to feasibly compare different methods for doing things. Does the 7.5 seconds include the flushing to disk? Yes, it would. So the assumption here is that all of these pages that are written don't go via the operating system, they go straight to the disk, and flushing a page to disk costs that much time. If I had a database, we could actually test it, but I think, Curtis, you're right. It's not going to take anywhere near 7.5 seconds to run a query like this. But the critical thing is how many pages we read, how many pages we write. Let's see, maybe I can find a database with an approximate size table. I'm going to look at a pizza database before. Remember last week we wrote a thing to tell us how many tuples were in each table, and why I put backslash at the start of that line, I'm not sure. And obviously I haven't loaded that. Let me just load it. Let me see if I can remember the file name. Bingo. All right, so let's go back here. And we haven't got 10,000 tuples in a single table there to try this exercise. But there are plenty of other databases. Look at them all. Maybe CMap. I know that's got some large tables in. Whether it's actually got dbpop, I'm not sure. Clearly it already had that. So, oh look, there's some large ones. Here's I really need to know how big the tuples are, roughly. All right, let's have a guess. I might be able to estimate something that's going to trying to find, what kind of half-time affiliations. That's not spelled correctly. Maybe it is now. So like, what are you talking about? Seriously? Oh, what does that tell me? What's the inference I can make from the output of this? Still waiting. Yeah, correct. So obviously we're not storing fractions here. Aha. Maybe F date. Affiliations. That would do. Oh, I know what I meant to do. 2010, a lot of 2010. 2011. Probably should have just extracted the year, 2012. All right, so let's try. affiliations, and trying to work out roughly half of the affiliations. Well, that'll do. All right, so the analogy to what we did before was insert into new affs from this query here, except oh, damn. And I do. All right. One thing that's going to affect the timings here is that I've already been poking around the affiliations table, and a whole lot of it is going to be buffered. So, so the time is definitely going to be less because there's not going to be as many real reads. All right, so where's that gone? Can't read that. Okay, so if you want to time Postgres queries, pretty sure that's the way you do it. I know it doesn't exist. I wanted to create it. Oh, interesting. I thought you could just insert into a table based on a query. Let me just check the Postgres manual. I must use the wrong thing. Maybe I needed to say from or something like that. SQL commands, insert. So at the moment I'm looking at Postgres, trying to find the right syntax. Insert into table. No. Right, so the question is, when we exit a database, will the buffers, I assume, used by that database get evicted? The buffer pool is actually in shared memory, and it's available to all the Postgres processes. And as long as there's a Postgres process running, and there's always going to be that process that sits there to pick up authentication requests. So open a database as this user with this password. Notice that we're avoiding everything to do with authentication on Greek, and the way we're installing the databases is just bypassing all that stuff. Yeah, if you terminate the main Postgres process and then restart it, that'll be like a cold start, and you start with the buffer pool initially being create table. Oh, it's create table, is it? Thank you. Cool. No, really, so my question, my whole question is wrong. UFs as, yeah. All right, notice units here, 13 milliseconds, so it's way less than 7.5. But of course, things we don't know. We don't know how many tuples per page, so we're not sure how many page reads and page writes. But there's a lot of tuples, and there's a fair bit that will take up a fair amount of pages. I'm pretty sure that we can actually find out how many pages are in rel pages. Just to make sure that it's the table. What? Oh, really? Why? Did I spell affiliations wrong? I did. All right, 114 pages. It's way less than 500. Yes, thank you. All right, in any case, it's pretty fast. And even if this was 500, I doubt that would come anywhere near 7.5 seconds. Now, of course, the reason for that is that there's a whole lot of buffering going on, so that it doesn't actually have to read from the disk most of the time. That's interesting. All right, so I'll go back to, there should be a nice way to do this. I know you can share multiple windows, but the trouble is when you switch between them, it seems to drop the sharing on one of the windows. All right, there's a Postgres manual where I was looking in the wrong place. All right, so that should be create table s as select blah, blah, blah. I'll fix that. That's a reason for not putting the slides up in advance, because you find mistakes. All right, this is kind of a throwback to last time, but to last week when we talked about where the files lived, but also the file manager of Postgres has to handle all of this kind of stuff. And we did talk about the file manager in the videos. And in particular, one thing we certainly didn't talk about last time was forks. Now, maybe I can find some forks in amongst all these databases, because some of them, I believe, are quite large. Yeah. So GeoNames is pretty big. Well, it has some large tables in it. Have I got IMDb? If that's not the cut down version of IMDb, that's pretty big too. All right, so the question was, let's have a look at the pizza database. And, all right, in a Postgres server, have a look at that, find the directory containing pizza database, find the file containing people, have a look at that as much as you can, and let's see. All right, I'll stop sharing this and jump back to sharing the terminal window. And here we are inside the pizza database. All right, so that's the relations. First thing though, we were asked to find which directory holds the pizza database. And the way we can work that out, first thing we need to know, select look at the catalog where the name of the database is pizza. Okay, so that's the OID for the pizza database. And if you remember, and if you looked at the videos on the file manager, Postgres uses OIDs to locate the databases. So each database lives in a directory, or each public user database lives in a directory which is named by its OID. Okay, now in order to find that, we'd have to look in the PG data directory, and then we'd have to look in the base directory, because that's where the user databases live. So if I do an ls here, we've just got all these random numbers, but 14745 should exist. Oh, no, I should have probably done ls-l. Most of these things are directories. And that directory exists. And now we're looking at all of the files in that directory. And there's quite a lot of files, despite the fact that there aren't that many tables. So a lot of the catalog tables get copied into here, plus other database configuration tables. So we found the directory containing the, where am I? Oh, I'm in this directory. Right, I need to be editing the push D makes a stack of directories, so you can easily go back to where you came from. And I go down into exercise 2, and I edit this file called files, which I'm apparently already editing. That's interesting. Is that here? No, it's not. Must be editing it in some other window. Okay, examine the content of the PG data directory. We did that. Find the directory containing the PG, the pizza database. So that lives in $PG data /base/da. Right, and we saw there was a whole bunch of files in this directory, some of which contain tables. Well, I think pretty much all of them contain tables. Some would contain indexes as well. And since I've got a directory stacked up, I can go pop D, and that will take me back to this directory. Right, and I think it was that one. Was it not? Yeah. Right, so now we're in that directory and we can do an ls and we see all of these files. Right, so how do I find which of those files corresponds to the people table? All right, so we need to go and look in the catalog again. In this case, we look in the table that contains table information, class where, and remember Postgres maps everything to lowercase. So even though the question says capital P people, it's going to live in the catalog. It's going to be stored with a lowercase p. Rel kind equals R, where R means relation. So hopefully this will give us the OID of the files that contain people. Right, you can see the OID is kind of similar to the one for the directory, and that's because this was created when the database was created and the OIDs gradually increment. All right, so we don't need to be in there. 5, 2, 7. Oh. And there's a file which presumably contains data from the people table. Notice that it's also got an auxiliary file which tells you, which is FSM, short for free space map. Tells you where there's free space within the pages of that file. One thing that would be worth looking at is the size of these things. So this is 49152, and if we bothered to check, which we can use desk calculator. Pretty sure 192, yeah, that Postgres pages are all 8K bytes. So if we take the total number of bytes in this file, divide by 8K, it should tell us an exact number of pages. So there are 6 pages in this particular table. All right. Can we look at this file? Not particularly, because it's binary. And we'll have a look at the internal page structure probably in the next online session, and I'll make the video for discussion of the internal page structure tonight. One new message, all right. Ooh. A192 comes from the fact that Postgres pages are typically 8K. Yeah. There's another question that I don't think I answered. Does termination of PSQL completely empty the buffer? PSQL is a client process. There's still a server running, and the server will continue holding all of the pages that were buffered while PSQL was running. And so if you ran a PSQL command and you looked at a particular database and did a whole lot of select from that database, and then you quit PSQL, and then you came back into PSQL, probably all of the data that you'd been looking at, and assuming that you don't have a giant multi-user system where 100 other people may have just looked at different tables, assuming that you're the only person using it, everything will probably still be buffered. So if you try to do timing stuff, it's going to be pretty tricky. If you want to get reliable timing measures, it really needs to be done from a cold start, and that will give you a bit of a clue. So basically stop the server, restart the server. That will, as soon as you stop the server, all the memory it was using is gone. Well, it's not gone, but it's reallocated. When you start the server again, you're going to start with an empty buffer pool. And then while you're doing select, you're going to gradually fill up that buffer pool. 8192, let me see. I have a feeling, yes I am. That somewhere in here, that value is defined. No, it's not. Okay. So it must be defined in the source code. So if you want to change it, if you want to have smaller buffers or larger buffers, you're going to have to go and modify the source code and recompile the system. I could go and have a look, actually. All right, let's let's go and look at the source code and see if we can find where it's defined. I think. Yes, that's good. So here's my source code. Let's go into the source directory and search through all of the directories for the number 8192, starting from the current directory. Ugh, never fails. Ooh, look, there's a few. Wow, interesting. I'm a bit disappointed that there are so many uses of magic numbers. Yeah, no, that's not the one I was thinking of, but somewhere there should be a definition that says page size or block size is 8192. These are all annoying. Let me just get rid of them. There's still a few of them. I was going to say that's the one, but it doesn't. That looks to be... Oh, lec3. Okay, so that's a separate thing. I'm surprised 8192 isn't defined in a single place so that you can actually change it if you want. All right, it looks like 8192 hard-baked into a lot of the code. So that's it. Postgres uses 8192. And unless you want to put in a lot of effort, it's not going to be super easy to change. All right, now let's have a look. We're back here. This file is the data file for the people table. Now the people tuples, some of them have got people names, which are strings. And if you want to see if you can extract the strings from a binary file on Unix, there's a command called strings. And if I do that, it should start spewing out all of the strings that it finds in this particular file. Who knows how long that would take to install. Oh, so that's not going to run at all. Damn, I knew there was a reason I should have done this on Grieg. Right, any case, we could have seen the strings in the file. If you really want, let's see if this actually works. So there's another command that allows you to play with binary files. Aha. All right, and if we look through here, we can see there are the occasional string. In fact, looking through this, we could really decode the layout of the tuples and work out, which bits correspond to which part of the tuple. But I'm not going to do that now. But you can see that we've got names scattered throughout this data. So each of those names is going to come from a tuple. And I could have a guess and say, well, maybe the tuple starts from here and goes through to there. So that sequence of bytes represents a tuple, and the representation allows us to go to an individual byte and say that individual byte is the start of a value for a particular field in the tuple. But like I said, we'll talk about that next time. All right, so let's see. Find the file in this directory. Yes, we found it. Now, if you were to do this, if you were to create the pizza database, and in fact the dump for creating the pizza database is in the week 1 exercises in a directory called databases, and you can load it up. If you were to load it up, it's extremely unlikely that you'd end up with the same numbers depending on what else you've got stored in your Postgres cluster. All right, so that's the file for the people table. Examine the contents. Yeah, we use od-c. If you're on a decent machine, you can use strings. What are the other files in the directory? Well, we saw there are a hell of a lot of them. And if we wanted to, we could go through and work out what each of these things corresponded to. Let's just have a look at one of them. I'm assuming it's a relation from okay, so that's one of the catalog tables, and it's the constraint table, and it ends up being local because constraints are local to the database. Now, if we think about the sort of OID we saw earlier, yeah, I'll talk about that in a moment. We're likely to find this as one of the, great, really? Did I grab that whole thing? Oh, let's try this one. Oh, that's interesting. Beautiful. All right. Well, I guess those things are not exactly tables. They must be something else. It's a little bit surprising. The PG class table seems to contain most different kinds of database objects. So there must be some kinds of database objects that aren't in the PG class table. Let's just try one more. All right, there you go. Couldn't find it. If I really wanted to find out what they were, I'd go select rel name from PG class or select from PG tables. I'm pretty sure that PG tables doesn't store the OIDs. It's more of a symbolic view of things. Yeah. So it's a convenient, it's actually a view in the catalog, and it will give you a nice symbolic view of things, but you can't use the, or you don't get access to the OIDs. All right. Yeah. Oh, yeah. What if there are two databases containing people table? That's fine. They're going to be two completely separate files. They'll live under different directories because they're in different databases. They'll most likely have, well, definitely have totally different numbers, different file names. So that's not a problem. So tables are, if you like, local to the database where they're defined. And when you use something like PSQL, of course, the first thing you do is use, all right, the first thing you do is select a database. So that sets some context, and then everything else is done relative to that context. So all of these things, and in fact, if I were to go to another table, I'd probably find a people table, another database, I'd probably find a people table somewhere in there. And it would be, like I said, totally separate thing, different OID. It's located in a different directory. All right. Stop sharing. Jump back to sharing the browser. Be nice if you could just toggle between them, but that doesn't seem to work. Oh, are there any forks in any of your database? Okay, if you've watched the file video, especially the PostgreSQL file manager one, you would have seen that once data files get extremely large, Postgres puts an upper bound, which is 1 gigabyte, which is actually the maximum file size for Unix, or at least it was at one stage. So as soon as a data file reaches 1 gigabyte, Postgres, if you add any more tuples to it, will create a new file and add them into that. And the way you recognize these forks are that they've got .1 or .2. So it just keeps adding files. So you've got the the people file, that was 14756 or whatever, was the table data. It only had 6 pages in. If it had 6 million or 600 million or whatever gets you to a gigabyte, and you needed to add more pages to the people table, then it would create a new file, 14576.1, and so on and so on. And therefore it can create as many forks as you like, and therefore can create as large a data file as you like, modulo running out of space on the file system. Oh, that one I did. A fork is an extension of a table file. Yes, effectively. Now, places where there may be forks, because there are some fairly large tables, is this one. So you can see it's only got 2 tables, but each of them is pretty big, and I'm not sure whether I've got DB pop loaded. I do. And all right, GeoNames is the one. It's got 8 million entries, and that took a while to do the count of tuples in that file. All right, so let's see, select. Let's find that directory for that where. Okay, so here's the OID of the GeoNames database. One thing you can probably infer from that is that the GeoNames database was created quite a bit before the pizza database, because the OIDs are a fair bit smaller. Where are we? All right. So there ought to be a directory called that, or with that name. That's the GeoNames database.
Excuse me, you're spilling the slides.
Yeah. All right, good point. Yeah. Stop share, reshare, terminal. All right, so all I did was, well, let's go back here. I found a database that had a fairly large table, and I wanted to see if that was big enough to create some forks. So get the directory name where the database files are stored, happened to be that one there. And Did I CD into that directory? Maybe I didn't. Where am I? I'm in database. Oh yeah, all right. So yeah, so that's the OID for the geonames table. And oh, lo and behold, we do actually have a fork. So this table here is large enough that we have to create an extension for it. And I need to get the chat back up. We can't really, yeah, I fixed it. So yeah, the question was, fork is an extension of a data table. So if I was to look at these two things, one thing we could do is free space map. It's not a kind of fork, it's an extra file that tells you information about the data files. And there's also VM as well. So they're, if you like, metadata files associated with. Now, if we wanted to what? Did I add any? What? I thought I copied and pasted. Obviously not. It was this one here. 80848. Oh, am I not in the directory? Yes, I was just doing ls on that directory. Okay. Right, go into that directory and then I can do that. All right, so you can see this file is quite large, and because it got so large, we had to extend it by adding a new file, which also contains tuples of the same type as this first file. So it's really a single table. And if I was to check how many pages you can actually fit before you have to create a new fork, it's that many pages. Yeah, 130,000 pages. No, not every file needs a visibility map. Or not every table. It would get created, what's the context it would get created? Possibly after you delete some entries from a table. Let's just have a look. So we go back, so we've got a free space map. That's the only thing. Oh, there's a few SVMs. All of these things, I'm guessing, are catalog tables, but you can see that there's no VM for this table because this, I know for a fact, this table was created simply by doing a large number of insertions, and we've never deleted anything from that table. And you've got these other, sorry, what is visibility map? It's in the slides. It's a simple answer, which I'll go and take a look at now. Yeah, thanks. Oh yeah, that's all right. I thought it was used for vacuuming. So if a page if all the tuples in a page are visible, the vacuum process doesn't need to examine that page during its vacuuming process. All right, I think we've done that exercise to death. Let me go back and have a look at the next exercise. Go back here. Oh yeah, share that screen. That wasn't the tab I wanted, it was this tab. Okay. So I have to reopen the chat each time. All right. So buffers. Well, there's a question. If all the tuples are visible, it means we don't need a VM file. I guess so. If you want to find out the gory details, take a look at the Postgres documentation. And there's a section on vacuum, I believe. Where is it? That's how you find it. You do a search. And it helps if you spell vacuum correctly. Right, so you can have a look at the Postgres documentation to find out what's happening there. All right, but I want to take a look at another exercise. All right, so files, I think, so I guess the point I made in the videos for files is that given a file name, there's a way of using the catalog to work out what file you're dealing with, what file in the file system. Obviously, you know, if you've already opened a database, you would have got the OID for that database. You can then work out the OID for the file, which for the table. So let's say we're looking for the people table, we can get an OID for that. Given all that information, we can put together a file name, and then which is the data file for that table. And then we can open that file and start extracting information from it. So that's basically the mechanism that the file manager provides, a mapping from, well, one of the mechanisms that the file manager provides, a mapping from names like pizza and people to files on the file system which have names like these. And once again, I'm pointing at something that's not shared, right? Doesn't matter. If the tables were larger, the above analysis weren't. Oh, I got them in the wrong order. All right. So now we've got two relations, and we're going to do a join. Unfortunately, the query, the exercise doesn't say it's a join. So we want to find out how many customers are employees. So we obviously can do a join on the customer table and the employee table, trying to match ID values. All right, how many page reads occur? If we have only 2 buffers, if we've got 20 buffers, if we've got these different replacement strategies, and assume for the MRU and LRU that we're talking about a buffer pool with only 3 slots. All right, so a buffer pool is basically a large chunk of memory that contains a whole lot of slots that can hold data pages that have been read in from the data files in whatever databases we're using, in fact. The pages, the page slots can contain pages from a whole lot of different files depending on what databases the backends are accessing. So the buffer pool is shared amongst all executing Postgres processes. And since Postgres processes probably access a fair amount of data, the buffer pool tends to be very large. And you may remember last time I talked about setting up Postgres on a Mac. You had to increase the amount of shared memory that a process was allowed to ask for, because Postgres grabs a very large chunk of shared memory for its buffer pool. All right. So what's the effect of doing buffering? All right, so let's switch back to the terminal screen. Open up the chat again, and hopefully, did I actually use, damn, I didn't use popd to get there. All right. Work. So this is eventually, i.e. after this session finishes, end up on the website. A new message. Right. CD minus. Really? Nah, surely that doesn't work. Interesting. I must be old-fashioned to think we need push D and pop D. All right. Yeah. So here's the analysis for a join query. All right. So essentially what we're doing is maybe we do, well, let's assume we're getting ID and name. And yes, I could have used a natural join. Oh, that's it. That's what we're doing. And let's assume that, I guess it doesn't matter which table that comes from. And maybe that doesn't matter either. Okay, so in order to answer this query, we're conceptually going to look at each page in the customer table. In fact, more than conceptually, this is physically what we're doing. Look at each page in the customer table. For each page in that table, scan all of the pages in the employee table, and then once we've got 2 pages, one customer page, one employee page, we scan through all pairs of tuples and see whether any of them match, in which case we stick them in the results set. So I think in some of the slides I abbreviated that to something like, compare all pairs of tuples from each page. Oh, interesting. All right, so customer 10 pages, employee has 4 pages. If we have only, well, all right, so what's the pattern of access to these pages? Okay, we access the first customer page, and then we access all of the employee pages. Then the second customer page, all the employee pages, and so on up to the last customer page, and then all the employee pages. All right, if we've got 2 buffers, then clearly what we're going to have to do, and you can't do it with less than 2 buffers, of course. If you've got 2 buffers, you read the first page of the customer table into one buffer, and then you read the pages of the employee table one at a time into the second buffer. So every one of these requests, if you like, turns into a read because we've only got 2 buffers. We're not, effectively, we don't have buffering. All right. Oh, yeah, okay. It doesn't. We could equally do it the other way. And in this case, with 2 buffers, it wouldn't make any difference to the cost. But it may make a difference depending on whether the small table is in the outer for loop or whether the small table is in the inner for loop. That kind of consideration happens when the query optimizer thinks about how it might execute things. So if the query optimizer is forced to use a nested loop join, which is what this is, it would decide which table was best to be in the outer loop. All right. So yeah, so the cost, if we've only got 2 buffers, is 1, 2, 3, 4, 5 times, right, actually 4 times 10 plus 10. Okay, so we've got to read all of the customer pages. For each customer page, we read all employee pages, which on banking is what that says. Okay, so the outer loop gives us 10 reads, the inner loop gives us 40 reads, total of 50. All right, so if we got 20 buffers, then things become pretty easy. We read C0, put it in a buffer, then we read all of these pages and put them into buffers. We read C1, there's still plenty of free buffers. Here we're kind of assuming that no one else is using the buffer pool at the same time. So we can read that, put it into a buffer. These are already buffered. Then we read this, there's a free buffer for it, and then we get all of these out of buffers. So the only time we need to do a read is the first time we request a particular page. So we're going to read for that, 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 and then we never read for any of these subsequent requests, but we do have to read each of the subsequent pages in the customer table. So total number of reads, 10 for the customer pages, 4 for the employee pages, which is 14. And that is the absolute best cost for a nested loop join. Now, going back to the question about why does the customer come first, let's have a look what would happen if we had the employee table in the outer loop. So the number of reads would be number of reads. Number of reads would be 4 from the outer loop. That's probably the outer loop. And then for each of those, we're going to have to read in 10 customer pages, all right? And that's the inner loop. And in this case, that actually turns out to be less, so that's 44 reads. So it does make a difference which table is in the outer loop and which table is in the inner loop. And as I said, that's the kind of thing that a query optimizer would think about. All right, with 20 buffers, what was the next one? 3 buffers and a most recently used strategy. Okay, so page replacement strategies come into play where we don't have a massive number of buffers where we can hold everything, and we have more than one buffer per table, which is the case with 2 buffers. Right, so most recently used, as I said in the slides, determining usage is a little bit problematic. How do we know that a page sitting in memory has been used? Probably don't really know, because we might scan through that page and then scan through it again, but that's not going to have any effect on, well, we're not going to see it registered anywhere that we've just accessed that page. You could, but that would be quite an expensive thing to do. Every time you access the page, you have to update something that tells you when it was last accessed. So what we tend to do is to come up with a simpler way of measuring recency, and something that's pretty easy to do is to look at when the page was last released, and we'll use the release time as the most recent access time, if you like. It's an approximation, but it's simpler than having to update something every time you look at one tuple in a page. All right, so our buffer pool initially starts out empty, and there's no pages in any of the buffers. So here we've got 3 buffers, and we're going to always replace the most recently used page. So the first time when we read the first customer page, goes into buffer 0, why not? Then we read an employee page, goes into buffer 1. And then we process that pair of pages. Now, having done that, we can actually release E0, because we're done with it for the time being. We can't release C0 because we need that for the subsequent employee pages. So we can request a new E1, the page number 1 from the employee table. Now, always if there's a free buffer, you would use that. So that's what we're going to do in this context. We then process C0 and E1 and release E1. Now, E1 becomes the most recently used, and we're actually going to keep a queue where the most recently used is first, second most recently used, and so on. So it's priority queue. All right, when we request E2, because we use, first thing, all of the buffers currently have something in them. So we have to decide which one we don't, which one we can replace. Now we can't replace C0 because it's currently in use. E0 is not in use, and E1, the buffer containing E1 isn't in use either. So the most recently used strategy is going to say, all right, I'll take the buffer containing E1 and I will empty that out, and I will reuse that to hold the requested page. So E2 would end up in there. Right, so we process C0 and E2, trying to get all the join matches, and then we finished with E2, so we released that. So now that becomes the most recently used page. All the buffers contain something. We request a new page that's not currently loaded, so we replace the most recently used page by the new page. All right, we then process E3 and C0. We release E3 once we're done with it, and then we release C0. And I should scroll up, did I? Here, all right. So basically, when you say for each page in customer, there's a notion that you're requesting. So it's essentially that sort of bundled in with the for each notion. And similarly, we have to request and then once we finish processing that E page, we release the current E page. If I was to do for I equals 0, I less than number of pages in customer and so on, it might make a little bit more sense. But in any case, so when we're finished comparing all of the tuples in the E page with the tuples in the current C page, we can then release that E page. But we can't release the C page until we've looked at all of the E pages and compared them to that. But at the end of that, we would release the current C page. Okay, so that's how these request and release would be incorporated into this. All right, so where are we up to? Oh yeah, so we just finished processing C0 and E3. We release E3, then we release C0. C0 becomes the most recently used, and then we request C1, and it replaces the most recently used page, which is C0. The first thing we do after we've read in page C1 is we try to read page E0. Bingo, it's already loaded in the buffer pool, so we don't have to do a read. We then do the processing on those two and release E0. Where are we? I just lost my, sorry, we're release E0, so E0 is the most recently used. We then fetch E1, and that replaces E0, and so on and so on. And you can work your way through all of this. So you can see sometimes when we have a request, we don't have to do a read, but it's not every occurrence. It's just every so often in the iteration through the various tables. If we were to follow through, how many reads do we actually do? Well, if you want to do all of the tracing, why we use MRU? Because I said we were using MRU. The next example uses LRU just for comparison. So how many reads? Well, you'd have to do a lot more of this stuff to work it out. It's definitely going to be more than the 14, but it's also definitely going to be less than 50, which was the worst case scenario we had before with customer in the outer loop. All right, if you want to use LRU, then you can go through that process yourself again. So the lists are going to be in the opposite order to what they are here. So you can kind of think, in this case here, we're going to replace E0, which isn't even contained in the buffer pool. But in any case, you're going to get a different number of reads. Now, it's tedious to go through this process, so the obvious thing to do is to write a program to do it for us. So something that can simulate this, and that's what the next question was, lec3. All right. So I'll do a make. Oh my God! Another reason why I need to be on Greek, because I've got all these tools already installed. Maybe I'll do that. No, I won't install, because last time I did an install of that, it took 20 minutes. Where are we? All right. Put is just an alias I have for SCP, which saves me a bit of typing. All right, so let's go to Greek. Here. Okay, good. I am Jess. So that should give us week 2. All right. It didn't take long, did it? That wasn't installed in CS9315, by the way, so it's not yet accessible through the web. All right. Now the make will. This is what happens when you don't test before the ooh, really? Oh, that's ugly code. Must have worked on an older C compiler, methinks, but not on this one. Oh, that was in the same. So here's an example. Read the error message. Warning, type defaults to int. All right, it might be useful if we actually put int in here, so we weren't relying on that. And page in pool. I'm kind of wondering about that. Oh, well, let's hope that we end up with a binary that actually works. Implicit declaration of function string compare. And we know that string compare requires us to hash include the string functions. Apparently it didn't used to. All right, let's see. Beauty. All right, so I've got a program called JSIM, JSIM, Q, all right, which gets used like this. Now this allows us to simulate a join where I've got that many pages in the outer loop, that many pages in the inner loop, that number of buffer pool slots, and we're using this strategy. And what C is clock sweep, which is a strategy that Postgres users. All right, so we could actually test out 10 for 2 slots, and the strategy doesn't actually matter here. Let's just take M, see what happens. All right, so you can see 50 reads. That's good. That's what we got before. And let's see what happens if we put the smaller table in the outer loop and the larger table in the inner loop. We get 44. All right. Now we did some all right, if we've got 20 buffers, so we'll stick with our 10 pages in the outer loop. We end up with 14 reads and we avoid 36 reads. Really? That should have been big enough to hold everything. Oh yeah, that's right. That's right. I've gone mad. All right. So we had 50 requests. We're always going to have 50 requests with 10 in the outer loop and 5 in the inner loop. And this is the minimum number of reads that we can possibly do. So we have to read all 10 pages from the outer table and all 4 pages from the inner table. So most of the time we were finding the page that we wanted already loaded in memory. And you should always have, in this case, we're not doing any writes, number of reads and number of hits should add up to number of requests. All right, so let's see, we had that 3 buffer case. And that ends up with 38 reads, 12 hits. We saw that we were getting some hits when we were using MRU. Is LRU any better? And I should give you 2 minutes to think about whether it's going to be better or worse, but I'm in a hurry, so I won't. I'll just run it. So 50 requests, always the same, 38 reads, 12 hits. Let's see what we get here. Wow, LRU is a dismal failure. So to answer your question, why not LRU? Because it effectively does no buffering at all. It's like having 2 buffers. You can go away and, well, you'll have this program so you can run through and see what it's actually doing. And I think even if I used clock, which I may or may not have implemented, same problem. All right, so LRU, yeah, exactly, sequential flooding. Someone's looked at the video and read the slides. So sometimes LRU is dismal, sometimes MRU doesn't work particularly well either. I have heard of DBMSs that just use random selection. So the reason we're worried about which page to replace is that potentially we have a number of possible victims. So if we're talking about the page to be replaced as a victim, there may be a number of pages that are equally good to replace. So we have to make a decision about which one to replace, and that's what this MRU, LRU, and clock sweep are all about. If you don't want to make the decision, you just replace a random one from the replaceable pages. And replaceable pages are pages that are not currently in use, so they got a pin count of 0, and that's pretty much it. So if you can find a whole bunch of pages with pin 0, and you can't be bothered using any kind of strategy for replacing, you could just make a random choice out of those pages. I'll let you have a look at how clock sweep works. So Postgres doesn't use LOU, doesn't use MOU. It uses its own strategy, which kind of, it has some elements of recency, but from what I said before, if you want to talk about LOU and MOU, you have to maintain a list, and that's extra memory. If you wanted to use random replacement, you would need to build up a set or a list of possible victims and store that somewhere. What the clock sweep strategy allows you to do is not have to deal with any of those auxiliary data structures. So it just scans through the buffer pool until it finds a suitable victim and then chooses that one. And the fact that it continually cycles through the buffer pool means that you never sort of get stuck always replacing the first one, for example. So it's pretty smart strategy, has minimal overhead, and yeah, works pretty well, apparently. Yeah, let's try with more buffers. Let's have 10. Using clock sweep. All right, and let's compare that to most recently used 14 reads, which is better. You know what I should be doing? I should be piping it through tail -5, I think. Okay, so then we can do a comparison more easily. Clock and LRU. Okay, so clock isn't quite as good, but it doesn't quite have the overhead that the other two do, or it has less overheads. And if you had a different number of buffers, you'd end up with quite different results. So I guess you'll have the code for that when I install it on the website. You can play around and work out what's the best kind of strategy. Is there anything interesting in the code? Right, so the buffer pool interface is pretty much the standard. Initialize the buffer pool. That basically means allocate space for all the buffers. How many buffers? That many buffers. Good question. Can't remember what that is. We'll have a look at the code in a minute. Request page from the buffer pool, and the page ID is given presumably by int, and release a page from the buffer pool. I remember what the char is. It's actually the name of the relation. So these two components together allow you to work out a unique ID value to identify the page in the buffer pool. And this would be similarly, this would be the name of the table. Or not. No, now I'll have to go and have a look. And then having a look at the current state of the database and the total usage. Now I'm intrigued myself to find out what that char is used for. All right. Oh, it's a cycle strategy. Okay, so maybe it's not quite clock sweep. But it has elements of clock sweep. All right, for a given buffer, we need some information about the buffer, the identifier, which is going to be the page ID plus the name of the table. PIN is how many transactions are currently using this buffer. Has it been modified? And this is the actual data itself. So here we've kind of got, well, we've got a link to the buffer inside this. This is really buffer metadata. This is the actual buffer, or at least it's a pointer to the actual buffer. So a bunch of information about the buffer pool. This information up here is for each individual buffer. And the other one is for the pool as a whole. Page in buff. Okay, fine. What I wanted to see was, you can have a look at all this, get next slide. Where's the initialize? Ah, here, init buff pool. Okay, the strategy, of course, all right. Whether it's least recently used, most recently used, or cycle, which is kind of a cut down clock sweep. All right, so we allocate some space for the buff pool object, and then we need to eventually allocate space for all of the individual buffers, which we do down here. And here we're just setting up, initializing all of the stats. And here we're making sure that all of the metadata about the individual buffers is initialized as well. All right, a request does the kind of usual things that you'd expect. It has to first check, is the page already in the buffer pool, in which case, beauty, we don't have to read anything. We've already got that data. If the page isn't already in the pool, then we check, is there a free buffer? That'd be the first thing we'd use. If there's not, then we've got to work out which buffer pool slot we're going to use. So this is the thing that finds the victim. And eventually we can work out that we've got a slot to, or we've got a particular frame in the buffer pool, and then because we've just had a request, we have to increment the pin counter, because basically what the request means is somebody else wants to use this page of data. Obviously, we don't leave it in the used list if it was already there. Can we download the C document? Yes. Well, in half an hour when I copy it across, you will definitely be able to. And then we return which slot we found the page in. So one of the things we were doing up here was checking, is the page already there? That will give us a slot. If we found a valid slot, then, okay, we're done. And we increment the hits counter. So that, and notice this is the global buffer pool stats page. So we didn't have to read a page in this context. If the page wasn't already in a pool, then we do have to do a read. This is initializing a page if you conceptually have to read it in. And this is setting up the ID. So once we reach this point, the page we want is located in the buffer pool in this location, and we increment the pin counter, as I said, make sure it's not on the used list, and then we dump out the state of the buffer pool. You can comment that out if you don't want that real long set of stuff. Release page is pretty straightforward. Basically, well, you're counting the number of releases, that's fine. You check whether the page already exists in the buffer pool. If it doesn't, you shouldn't be releasing it, so that's an error, which is why we have this assertion here. And then all we need to do for a release is decrement the pin counter. We don't need to do anything else. We simply leave the buffer leave the data in the slot in the buffer pool. Okay, and I suspect this make available doesn't mean clean out the buffer. It basically means set it to a potential victim state, I think. So next time someone makes a request and the buffer pool's full, then that's a potential victim. All right. You can find similar stuff in the Postgres source code if you go looking for it, but it's wrapped up in a whole bunch of stuff and it's a lot less easy to see what's going on than this code. All right, it's 4 o'clock. That'll do for today. I will take all this stuff and put it on the website, and in future, I will try to put the exercises up on the website before the lecture starts. All right, that's it for today. I will see you on Thursday at 2 o'clock. Just checking, thought there might be no one left. All right, stop sharing, stop recording. Okay.